All right, guys. Good day, everyone. So we're going to be doing some thermodynamics examples today. They are all based on Cengage, and there are a few things that you need to remember. The main thing that we're going to be using a lot is PV equals to nRT. Okay. One of the problems in the assignment gives you an ideal gas, right, that is inside a container with a piston where you have the mass of the piston. So the mass of the piston is of 8,000 grams, which conveniently enough, that's 8 kilograms. And the area is of 5 centimeter cube. Square, sorry. Which, to change area from centimeter square to meter square, is not 0.05. Is 5 times 10 to the negative 4 meter square. You have to divide by 100 twice. Okay? How much work is done on the gas as the temperature goes from 25 to 305? So the initial temperature is 25 degrees Celsius, and the final temperature is 305 degrees Celsius. Okay, and the given number of moles, 0.108 mole. So this problem, you need to use a definition of work. Okay. Work is equal to the pressure times change on volume. To find the change on volume, you need initial volume, final volume, and you are going to need the pressure. Pressure is defined as force over area. The force is basically the weight of the piston. 8 times 9.8. The area is this. So I can find the value of pressure in pascals or Newton per meter square. So I do 8 times 9.8 divided by 5. Okay, so I get 15.7 times 10 to the 4 Newton per meter square. Newton, sorry. That's Newton per meter square. That's pressure. To find the initial volume and final volume, I use this. So we have pressure, which in the problem, I'm going to show you guys now the problem. There, right? So in the problem, the pressure, it says there, you get a pressure constant. So we are going from 25 to 305. So we have to change, or we have to find the volume using the ideal gas equation. Now, to use the ideal gas equation, we have to change the temperatures. Initial temperature in kelvins. So 25 plus 273. We can just use that. And for the final temperature is 305 plus 273. So in kelvins, it will be 298 kelvins. And this will be 578 kelvins. Those are the initial final temperature. So then pressure right? Pressure. Or actually, guys, if you think about it, volume, initial volume is NR, initial temperature over pressure. But pressure is constant. Final volume is NR, T final over same pressure. So when I write this equation, look what happens. One is pressure, parenthesis, nRT initial, nRT initial over pressure, well, final, sorry, minus nRT initial over pressure. Why am I doing that? Because pressure cancels, so I don't have to worry about that. So then my work is just nR, N is 0.108, R, 8.31 joules per mole per Kelvin, right? And then temperature final, so this minus this. So 578 minus 298. I don't know if you guys can see that. I'll put that in there. There. Okay. So that's the equation for work. So my work will be just that. So let's take a look. Now, the work is done on the gas. Oh. Okay, times 0.108 times 8.31. Ah, 578 minus 298, 280 times 8.31 times 0.108, 108. Oh, what am I doing? So I get, let me see here. Oh, 0.180, sorry. No wonder. This is 0.180. Okay. So if I change that, this is 0.180. All right. Let's show you. So 578 minus 298 times 8.31 times 0.180, 420. If you round it, 420 joules. Now, that work will be negative because it's work done on the gas. So negative, okay? Now, by action reaction or by conservation of energy, the gas does positive work on its surroundings, right? This work for part A is negative, but then for part B, when they ask you what about the work done by the gas, will be positive on its surroundings, right? By action reaction, you think about conservation of energy as well. Okay, so that's one example there. All right. Let's do a PVD diagram. I want to show you that here. You have that diagram. It says the gas expands from I to F, and you have free path. If you go from I to F using IAF, right? IAF. AF, the work is zero. Why? Because it's a constant pressure. So you only have to worry about the work from I to A. Now, how do you go from I to A? Well, you're looking at the figure there. I'm going to write the equation here, and I'm going to show you. but clearly that's an isobaric process. Isobaric means at constant pressure, right? So you're going from 3 liters to 9 liters at 6 atmospheres. And you want it in joules. So remember, 1 atmosphere is equal to 10 to the power of 5 pascals, which does Newton per meter squared. And then 1 liter is equal to 10 to a negative 3 meter cube. You want is a units. So that's basically units if you think about it. So for IAF, the only work is from I to A. So from IAF, the work will be the pressure, 6 atmospheres, so 6 times 10 to the power of 5, multiplied by the change on volume. 9 minus 3, that's 6 times 10 to the negative 3. This is 3,600 joules. And it's expanding, so the work will be positive. Let me show you there on the whiteboard. That's basically how you will do it. Look at the unit conversions. All right. Let me just. Now IF. Let's share the screen again. How will you go from I to F? You are expanding the gas again. And just here quickly, just show you what you need to focus on. For IF, which is a line slanted, you are going from this point to this point. This point I, F. You are just looking at the area under the curve. So you're looking at this area. That's what you're looking at. You're looking at the area under the curve. Right? The points are still the same. From 3 to 9 liters. And this is from 6 atmospheres. And the F is at 1 atmosphere. Right? That's it. So for a trapezoid, right, the area is 6 plus 1. So the work will be 6 plus 1 divided by 2 multiplied by this, the height. It's a trapezoid. That's also 6. But hey, units, right? So let's write this again. This is in atmospheres. So this is 7/2 times 10 to the 5 times 6 times 10 to the negative 3. 2,100 joules. That's the work. Okay, so that's the formula for the area of a trapezoid. The sum of the bases divided by 2 multiplied by the height. And then you have to remember the units for, right? This is an atmosphere, so you have to use a conversion. And then the liter conversion to 10 to the negative 3. That's what you look here. Okay, so just the area under the curve for IF. It's pretty simple. And then the IBF, IB will be 0, and then B2F will just be 1 times 10 to the power of 5, 1 atmosphere times the 6. So that should give you 600 joules. This is a practice problem, so it's the same as the one you're gonna do in the assignment anyway. So different numbers. Okay, so that should be easy. All right. Here is also the solution there. All right. Oh, the work is on the gas. So all the works have to be negative. Okay, yeah. So since they ask you for the work, be careful with that. If the work is on the gas, all of these have to be negative, all right? Like in the first problem we did. Have to be careful on that. If it's done by the gas, it's positive. Okay. This is a good problem there. How do you get that value there? Like a balloon holding 4 moles of argon absorbs 915 joules and is doing 137 joules of work expanding to a larger volume. So what's the change in the balloon's internal energy? Okay. That is just the first law of thermodynamics. So we are going to use Q equals to W plus delta U, where delta U is the change of internal energy. All right? So remember, Q equals to W plus delta U, where that's the change of internal energy. We talk about that in the lecture. I did. There. So if you absorb, Q is equal to positive 915 joules. And the work is positive, is expanding 137 joules, and it's not by the gas. So the delta U is Q minus W, 915 minus 137. Let's take a look. 778 joules. That's an easy question there. But there's a reason why they give the moles of carbon. Calculate the change in temperature of the gas. So guys, since you are looking at the change of temperature, right, you have to use the equation for the internal energy. That's what I was talking about the other day or in the lecture, right? You have to use CV or CP. So we're going to use the equation delta U equals to N CV delta T. Okay? And in the problem, they give you 4 moles of argon. Let's do it here so you can see it. Delta U is NCV delta T for that particular process. N is 4 moles of argon. Argon is a monoatomic gas, so CV is 3/2 of R. Delta T is what you want to find. Delta U is 778. That's equal to 4 moles, 3/2 of 8.31 times the change on temperature. So then the change on temperature is just 778. Let's put it here. 778 times 2 divided by 4 times 3, 12 8.31. And then we have to use the calculator. 778 times 2 divided by 8.31 divided by 12. That's 15.6 is your change on the 15.6 kelvins. Okay. That is how you do that. Let's do a machine here. We have here a thermal machine or a nuclear plant with a power output of 410 megawatts. The rate at which energy must be supplied to the plant is is basically just energy supply, energy used, right? So the nuclear plant is using 410 megawatts, and the energy supplied by the plant is 1410 megawatts. So basically, let's practice another so you can see in different numbers. There. So the power output is 445 in that case, in that practice problem. And the supply energy, basically the Q hot, right, is, let's take a look, 1590 megawatts. So what will be the efficiency? Okay. The efficiency for a thermal machine or any machine is the work over QH. And the energy in the cold spot is the energy in the hot spot minus what? Unless you're talking about a refrigerator, remember, or an AC or an AC machine, right? So in that problem, the efficiency will be 445, and it's in megawatts, so you don't have to worry about changing units, over 1590 megawatts. So 445 over 1590, about 28%. And multiply by 100, don't forget. 20% efficiency. What's the energy expelled? QC is 1590 minus 445. So that would be 5, 4, 1145 megawatts. So you can do it with rates of energy as well, not just energy. Oh, can do it like that. Using these equations here, efficiency and QC. Not bad, right? Not bad. So pretty much that's, I might do another video with a diatomic gas, all right? But I kind of cover most of the examples that you kind of are going to see in the assignment. And then after this, you're gonna have the exam for these first 3 chapters, okay? If you have questions, please make sure that you show up to the office hours, okay? I wanna do one more point like this. Okay, I think the PV diagrams, and then using the ideal gas law is clear. Just be careful with the sign of work. Be careful with the first law of thermodynamics, the units, all right? If you're using atmospheres, you have to change to Pascal, liters to meter cube. Those are little things that you have to be careful, because if you have the wrong units, you will get the wrong answer, okay? So expect another video with maybe 2 or 3 more examples, and then I will start making a video for the next few chapters. All right? Okay, guys. I'll see you guys later on the next video. Have a nice rest of your day.